So in our previous video, we were working on this problem of a cylindrical can with a volume of 200 cubic centimeters. And we used the second derivative test. You can look that up, by the way, in your notes. The second derivative test to locate an absolute minimum of x equals the cube root of 200 over pi. And now we're ready for our last step where we're going to finalize and draw a conclusion. We have found that x, which represents the radius, by the way, of the can, is a cube root of 200 over pi. All right, and that would be the value for x that would minimize the surface area. So to find y, which is going to be the height, we're going to use y equals 200 over pi x squared that we acquired from step 2 in the previous video with this particular x. X equals the cube root of 200 over pi. That gives us y equals 200 over pi times the cube root of 200 over pi parentheses squared. That simplifies to 200 over pi times 200 over pi all to the 2/3 power, and then we're going to simplify this complex fraction by multiplying by 200 over pi to the 1/3 over 200 over pi to the 1/3. Now when we apply that to the top and bottom, we're going to get y equals 200 times 200 over pi to the 1/3 over pi times 200 over pi to the first power, because we had to combine the two exponents. And then we get a further simplification to y equals the cube root of 200 over pi. Okay, and so y does equal the cube root of 200 over pi. That represents the height of the can. And as we've seen in so many of these problems, the x and the y are matching. Now, that's not always going to be the case in other types of problems, but for these, yes, it has been. Thus, the cost to minimize, the cost for the surface, the metal for the can, is minimized when the radius and the height of the can both equal the cube root of 200 over pi, and the units are centimeters.